Our estimating of parameters is not just limited to estimating means and variances and difference between means and variances in various populations. We can also estimate other parameters. So remember when we were talking about the binomial distribution, we were looking at situations where there was a favorable outcome and not. It was a yes or no situation. And we actually had a parameter there that was the probability that we had a favorable outcome in a given instance. Now, we can use techniques similar to what we were using to estimate means and confidence intervals for means and variances to estimate what that proportion, what that probability actually is. We can come up with confidence intervals for that proportion. And we can even look at the difference between two proportions and come up with confidence intervals for those differences as well. So let's take a look at some definitions, theorems, and equations that we're going to need to be able to estimate proportions for the binomial distribution. When we're looking to find a confidence interval for the parameter p, we can do so when our sample size is large enough and our proportion value p is suspected to be not too close to 0 or 1. And to do so, what we're going to do is take a proportion p hat of the successes in a random sample of size n. So we'll take the number of successes and divide it by n, and that'll be our p hat value. And q hat's going to be equal to 1 minus p hat, the same way q was equal to 1 minus p. Then an approximate confidence interval for the binomial parameter p is given by this p hat minus the z sub alpha divided by 2 that we've been seeing a lot of, times the square root of p hat times q hat divided by n. That's going to be the lower bound, and then the same thing with a plus instead of a minus will be our upper bound, and p is going to fall somewhere within that confidence interval. So our z sub alpha divided by 2 is the same as we've had it before. Now, like I said, this is when our n value is large enough, so our sample size is large enough, and our proportion is not too close to 0 or 1, or not suspected to be too close to it. So one thing that we check to make sure that we really can use this fairly reliably is we check that n times p hat and n times q hat. So n times p hat and n times 1 minus p hat are both greater than or equal to 5. And if that's the case, then we feel relatively confident using this technique. Now, this is what's considered method 1 for determining a confidence interval. There is also a method 2 that is computationally much more complex. So I'll leave it to you to look in your book to look at this more complex method and see what's going on with it. We'll be working pretty exclusively with method 1, though. Now, as we've had with previous ideas of finding confidence intervals, we have a couple of theorems that follow with this as well. Our first theorem is that if we're using p hat as an estimate of our parameter p, we can be whatever percentage our confidence interval we were working with is confident that the error will not exceed that value that we're adding or subtracting from our p hat value to determine our confidence interval. Our second theorem tells us that if p hat is used as an estimate of our parameter p, then we can have our confidence interval amount of confidence that the error will be less than some specified amount, so it lets us choose the amount of error, and then we can solve for the sample size we need. Now remember, as our sample size grows, the same percentage confidence interval will shrink. So the smaller our sample size is, the larger our confidence interval needs to be, and vice versa. So this allows us to determine just how big our sample needs to be. We also have a theorem that allows us to decide that we can be at least our confidence interval amount of confident, that the error will not exceed a specified amount E when our sample size is n equals z sub alpha divided by 2 squared divided by 4 times E squared. And this all is a matter of p hat and q hat are going to be two fractions that add up to 1, and when we're at our worst case scenario, they're both equal to 1/2. And that makes p hat times q hat be 1/4. So if we substitute 1/4 into our previous theorem, then we end up with this new equation for our sample size. And if p and q are actually further away from 1/2, then we can be even more confident. Now, when we're looking at the difference of two proportions, when we have a large enough sample size, and again, our p-values are far enough from 0 and 1, then we can use this technique. So given p1 hat and p2 hat are the proportions of successes in random samples of size n1 and n2, respectively, and we find q1 hat by taking 1 minus p1 hat, and we find q2 hat by taking 1 minus p2 hat. Then we can get our confidence interval for the difference of the binomial parameters by taking the difference of p1 hat and p2 hat and subtracting z sub alpha divided by 2 times the square root of p1 hat times q1 hat divided by n1 plus p2 hat times q2 hat divided by n2 for a lower bound, and adding that same product for an upper bound. And again, z sub alpha divided by 2 is the z value leaving an area of alpha divided by 2 to the right. Now again, we need large enough sample size, so large enough n's, and p1 hat and p2 hat need to be far enough from 0 and 1. So again, we should check that p1 hat times n1 is greater than or equal to 5. q1 hat times n1 is greater than or equal to 5. n2 times p2 hat is greater than or equal to 5. And n2 times q2 hat is greater than or equal to 5. If all four of those products are greater than or equal to 5, then this technique will work for us.